Um,
Okay, so hold on one second. Okay, so we do have an exam coming up next week. And I have not, I guess I'm open to delaying it a week, but I don't know if that's better or worse for you guys. So I just wanted to see how you felt about it. I would like to finish up with chapter 4, honestly, before we do the exam. But if moving the exam like makes it so that you have, you know, I don't know, more overlap with other classes or something like that, then I'm fine with having it next week as well. Okay. So nobody has any like major objections to moving it back 1 week? Is that right?
Sorry, what was the day you said?
So it would be on April 22nd if we moved it back 1 week. Okay, so doing it next week. Okay, maybe we can have a vote. Okay, so there should be a way for you to like vote yes or no. I know that this exists. I don't know how to tell you how to do it though. Let's see, maybe it's under reactions. Yeah, it is. Okay, so if everyone could find the reactions button and vote yes or no. So yes would be you want to move it. No would be you want to keep it next week. Okay, so I think we had more yeses than nos, but they were like in different, they kind of like faded away. So, okay. I guess we will, I don't know. I guess we'll move it. Unless you have it was 5 yes, 4 no. Okay, thank you for keeping track. Yes, great. Okay, so we will move it to April 22nd. And I do hope that we'll be able to finish with chapter 4 before then. Not that we'll have the entire chapter 4 on the exam because, you know, I'll give you some time to learn those things, but yeah, I want to get through it. Oh, okay. I see. Okay, well, if you have any strong objections, you can email me about it. About the final project. Yes. Okay. I will post some like a handout with like detailed instructions, or maybe not super detailed, but you know, some instructions on how to do that, and some due dates as well. So final project. And then next week I'll post a study guide for the exam. Okay. Yeah, okay, gotta get this going. For the Yeah, I'll just put that on the handout. Okay. Oh. I should actually plug this in so it doesn't die on me. So give me 1 second. There we go. Okay. Okay, here we go. All right, so we last time had just started section 4.3, which is on linear independence. So the definition for linear independence was the same as the one that we had in RN, right? So I won't go over that definition again since it is exactly the same, but we're gonna do a few more examples, right? So we had 2 examples last time. We saw that, we'll just to review, so this is section 4.3 on linear independence. And we had 2 examples. The first one was the collection 1, sine of t, cosine of t. These are vectors in the space of all real valued functions. So we called that F, right? And this is linearly independent, this collection of 3 vectors. And then we had another example where we saw that 1 sine, okay, why is this? Sine squared of t, cosine squared of t was linearly dependent, or is, I guess, linearly dependent. Okay, so the script f, this thing right here, this is the space of functions. So that's why we use an F, just to stand for functions that map R to R, right? So from the real line to the real line. Okay. Let's see. Okay, so those are those 2 examples that we looked at so far. Remember that in F, this vector space of functions, the 0 vector, or we'll just write it this way, 0 is the function that is constantly 0. So we can write that like this, right? So the function that is 0 for all values, that's the 0 vector in this case. Okay, so let's do another example. And so here we can look at, we'll look at some vectors in P2. So this is going to, so our vector space V is just the polynomials of degree less than or equal to 2. And we want to know, is this collection, which I will write down, 3x minus 4, x squared plus 2, and x minus x squared. Is this linearly independent? Okay, so remember that, so if we give these some labels, so say that P1 is 1, P2 is 4x plus 3, P3 is 3x minus 4, and let's see, P4 is x squared plus 2, and P5 is x minus x squared, right? So just to give them some labels so that we can write this down, what it means to be linearly independent is that, here, let me put it this way. Linearly independent means that if you have a linear combination of all of these guys, I guess I'll write it all the way out. So there's 5 of them. Equals 0 means that all of these constants are equal to 0, right? So we could put it this way. If this occurs, then all of those constants involved are equal to 0. Okay. So how we figure this out for this particular situation is, well, first let's set up the linear combination like this for some arbitrary constants. So we know that this is going to be equal to 0. So I'm just going to put the 0 on that side. And then we have C1 times P1, which is just 1, plus C2 times P2, which is 4x plus 3, and C3 times 3x minus 4, and C4 times x squared plus 2, and C5 times x minus x squared. Right? So that's just the linear combination. And then if these are linearly independent, then we want to show that all of those constants have to be 0 in order for this equation to be satisfied for all x, right? Okay, so what we can do is just multiply this out and group the terms. Let's see. Could you also write this as, yes, you could do that. Right, but we haven't talked about that quite yet. Yeah, so we'll talk about expressing things in terms of a basis a little bit later. Okay. Yeah, I know, it's very strange. You guys can still hear me though? Okay, well then I guess it doesn't matter. Oh well, okay.
You can try turning it off and on again. Sometimes that works.
I will try that. Okay. Okay, yeah, cool. Thank you. Good tip. Okay, so like I said, we can just multiply these out and group them. So we would get, I'm just gonna try and do this in one step. So looking for constant terms, we have C1, we've got C2 times 3, right? So 3C2. We've got C3 times minus 4, so minus 4C3. We've got C4 times 2. So that's plus 2C4. And then there's no constant term in the last one. So these are all of our constant terms. Next, let's look for the x terms. So we've got C2 times 4x. So 4C2. We've got plus 3C3 and plus C5. Plus C5, yeah, times x. And then x squared terms, there's 2 of them. So we got plus C4 minus C5 times x squared. Move this over. Right. Okay. And so if this is going to be equal to 0 for all x, that means that each of these individually should be equal to 0, right? So we get C1 plus 3C2 minus 4C3 plus 2C4 equals 0. And also, might as well line these up. 4C2 plus 3C3 plus 5, or plus C5. And C4 minus C5 equals 0. Right? So we end up with a system of linear equations, right? That we can solve, right? So if we wanted to look at the matrix that represents this system, we would get 1, 3, minus 4, 2, 0, 4, oh, sorry, 0, 4. 0, 4, 3, 0, 1, and 0, 0, 0, 1, minus 1, and then augment with the 0 matrix, or 0 vector, sorry. Okay, so we have something that's already in row echelon form, right? So does this have a unique solution?
No, because we got free variables.
Exactly. No, because, oh, what's no unique solution? Oh, wait.
Because it's in R3.
Yeah, so there's not even enough entries in the columns to have a pivot in every column. So no unique solution because we necessarily have free variables, right? And that means that we can find, and we could use this to actually find some constants C1 up to C5 that give us a linear combination that's not all equal to 0, where the constants are not all equal to 0, right? That's what I mean. Okay, so, right. This means that the original collection that we had is not linearly independent. Wait, okay. Independent. Is that part clear?
I feel really confused because some things are so fundamentally different from what we've been doing all semester. Like, I don't understand thinking of a polynomial as a vector. It doesn't make sense to me. And then we're allowed to jump just straight to doing things that we have been doing. So like, we can't write the polynomials as a vector. That's not allowed. But then we do get to make an augmented matrix. And I feel like confused why we're allowed to do some of the things we've been doing all semester and not others.
Okay, so we can write these, if you want to, we could write these as vectors. I just haven't And we can do that in a second. If you want to like circle back to this problem and we can do it using vectors, if that would make you feel better. The reason why I went from here to an augmented matrix, so this is not like, this is just noticing that we have to solve a linear system, right? And then just writing it as an augmented matrix. So it's not like the same thing as, you know, creating an augmented matrix from the vectors after you express them as vectors. I don't know if I said that in perfect words, but hopefully it made sense what I'm trying to say. Okay, cool. Okay, so, right. So this is an example where we do not have linear independence. And okay, so now we're going to talk about bases and then talk some more about polynomials. Okay, so a basis for an arbitrary vector space V is a collection of vectors. Oh, I'll use V. So this is a basis for V if you have two things. So these are the same as what we had before in our definition for basis. So we need them to span the space. So the span of this collection is equal to the entire space V, and the vectors are linearly independent. Okay, and again, we can think of this as a basis. We can think of a basis as a maximal linearly independent set. So it's maximal in the sense that it spans the whole space. So any vector in that space can be expressed as a linear combination of these V1 up to VK, right? And it's linearly independent, right? So we have those two things, right? And let's do an example. Okay, so for example, if we look at polynomials of degree n, there's a standard basis, which is similar to the standard basis in Rn. Remember, the standard basis in Rn is all of the coordinate vectors. Boom. Maybe let's write that down first so we can compare it to Pn. So in Rn, the standard basis is the collection of E1, E2 up to En, which is all of the vectors 1, 0, 0, 1, and so on, right? Until you get down to the one with 1 in the last coordinate, right? These vectors, which we called the coordinate vectors. Okay, and we have other bases as well, but this was the standard one. Okay, now we have Pn, which is polynomials of degree n, and they also have a standard basis. And that will be the, so let's just write this as B is basically all of the powers of x, right? So 1x, x squared, all the way up to xn. So you could think of 1 as x to the power 0. And so then you get, these are all powers of x, right? Right, yes. The basis is a maximal linearly independent spanning set. Yes.
Okay, cool. I was just wondering because it said linearly independent set, and I didn't know if we needed the word spanning in there, or if maximal conveys that.
It does, but maybe it's a little bit better to say spanning as well. Yeah.
Cool. I'll just put it in parentheses.
Okay, yeah, that's fine. Okay, so this is a basis. So hopefully it's not hard to see that this does span Pn, because for any polynomial, P of x, which has the form C0, C1x up to Cn x to the n, you could write this as a linear combination. In fact, it's just straightforward. It's just you take all of the coefficients to be the coefficients that you use in your linear combination, right? So, so the span of this collection is Pn. Okay, so that's the first part of the definition. So if we're trying to show that this is actually a basis, right? So it does span the space. We want to show that these are linearly independent. So we want to show that this collection is linearly independent, right? Okay, so if we have that, we have a linear combination of these guys to Cn x to the n. If this equals 0 for all x, then we can just plug in x equals 0, right? If x equals 0, we get C0 plus a bunch of zeros, right, equals 0. So that first coefficient must be 0, right? Okay. So we just plugged in x equals 0 to the equation. To get the other, so we want to show that all of the other coefficients are 0. We can do a little trick. So if we know that, so now we have knowing that C0 is equal to 0, we just get C1x plus C2x squared up to Cn x to the n equals 0 for all x, right? Okay, so what we can do is we can take the derivative of this equation on both sides. And of course, the derivative of 0 is 0, but when we take the derivative of the left-hand side, right, we get, well, it's a polynomial, so the derivative is just C1, 2C2 up to n, Cn x to n minus 1. So C0 can't change, right? It's a constant. So if it is 0 for x equals 0, then it has to be 0 for all values of x.
Okay, I guess, sorry, I'm just confused because I don't, understand. Isn't it like a theoretical? Okay, we can keep going. Sorry.
Okay. So the coefficients are fixed, right? They can't vary as x varies. So if they are equal to something when x is one value, then if you plug in x equal, so if they're equal to c0 is equal to 0 when x equals 0, if you plug in x equals 1, it still has to be equal to 0, right? Okay. Let's see. Okay, so here we are. We have this equation now, and we can, so I'm just going to copy it down here. Skipped an x, right, up to n times cn times x to the n minus 1 equals 0. And then we do the same trick where we plug in x equals 0 and and then we get c1 plus 0 plus a bunch of zeros equals 0, which means that c1 also equals 0, right? And then we have 2c2, knowing that c1 is equal to 0 as well, plus a bunch of other stuff. So n cn x to the n minus 1 equals 0 for all x. And then we keep going. So we just take the derivative again, and we just pick them off one at a time and prove that all of those coefficients have to be 0. Right? I guess technically you should use induction to show this, but we're not going to. We're just going to. Okay. So we have that this means any linear combination of 1 up to xn, all of those powers of x, has to have all of the coefficients being 0, meaning that that collection is linearly independent, right? So this shows that this collection is linearly independent. Okay. So, remember that. So here we have another definition that we've had before. So this is the definition of the dimension of a space. So we had this for subspaces, right? But now we can talk about the dimension of any abstract vector space. So the dimension of an abstract vector space V is the number of vectors in any basis of V. And although you can have many different bases of a vector space, the number of vectors in it is invariant. This number is invariant, meaning it just doesn't change from basis to basis, right? Okay, so for example, the example that we just did that showed that 1 x squared up to xn is a basis of Pn. This means that the dimension of Pn is n plus 1, right? So we have n plus 1 things in that basis, so the dimension is n plus 1. Okay, so let's see. Okay, let's do another example of, or actually, do I want to? Yeah, okay, we'll just do this example. Okay, so this is an example of another basis for, so we'll focus on P2. So the question is the following a basis for P2? Okay, so so wrapped into this question are two questions. So does it span? So does the span of this collection equal P2? Oh, down, I guess. Oops. And are they linearly independent? Okay, so I want you guys to try this yourself for like a little bit just to see how far you are able to get, and then we'll talk about the answer. Okay, so how is the problem going? Okay, so let's go through. Does anybody have an answer?
I mean, I was able to get that the set is linearly independent.
Okay, that's good. Right, so that's half of it. Okay, well, we'll get to that, but let's start with the question of whether it spans P2, right? So what we want to do is, given an arbitrary polynomial of degree 2, so let's say it has coefficients a0, a1, and a2, we want to write it as a linear combination of these three polynomials, right? Okay, so what we can do is we can look at what if we set this equal to some linear combination of these vectors. So it would be C0 times 1 plus C1 times x minus 1 plus C2 times x minus 1 squared. Right? So we want to figure out, so remember here that A0, A1, and A2 are fixed, and we're solving for C0, C1, and C2. Okay. Now, what we're going to do is multiply out the right-hand side of this equation. So just, I'm going to take this down here. So this is equal to C0 plus C1x minus C1 plus C2. If we multiply that out, that's x squared minus 2x plus 1. And then we can expand this out and combine the like terms. So C2, like that. We've got plus C1 minus 2C2 times x plus C2 times x squared. Right. And so if these are to be equal for all x, so they're equal as polynomials, then the coefficients of these have to be equal, right? So you get that C2 has to be equal to A2, right? You get that C1 minus 2C2 has to be equal to A1. And then you get that C0 minus C1 plus C2 is equal to A0. Okay, so we can take these and rewrite them, at least this part. So C1 is equal to A1 plus 2C2, and C0 is equal to C1 plus C2, or minus C2, plus A0, right? And then we already have that C2 is equal to A2, so we can get from this that C1 should be A1 plus 2A2, and C0 should be A1 plus 2A2, plugging that in for C1, minus C2 is A2 plus A naught.
Can you please give me like a moment?
Yeah, sure.
Okay, sorry, I just got lost.
That's all right.
Lost in the coefficient.
Yeah. Or let me, we can write this. Okay. So we have our solution. If you want something a little bit more concrete, what this means is that if, say, you have the polynomial, I guess let's just pick some 1 plus 2x plus 3x squared, right? This is a polynomial in P2. And here, a naught equals 1, a1 equals 2, and a2 equals 3, right? For this particular polynomial. And then our solution tells us what the C0, C1, and C2 should be to write this as a linear combination of those polynomials 1, x minus 1, and x minus 1 squared. So our basis, recall, is 1, x minus 1, x minus 1 squared. And according to our solution, p of x is equal to 1 times c naught. So maybe I'll write this out first. So c naught is equal to a naught plus a1 plus a2, which is equal to 1 plus 2 plus 3 in our case, so 6. C1 is equal to a1 plus 2a2, which is 2 plus 2 times 3, right, which is 8. And C2 is equal to just a2, which is 3. Great. Okay, and so putting this together with the with the definition of the basis and everything, we get that this should be C0 plus C1 times x minus 1 plus C2 times x minus 1 squared. So 6 plus 8 times x minus 1 plus 3 times x minus 1 squared. And if you multiply this all out and simplify it, you should get our original polynomial, 1 plus 2x plus 3x squared.
So we've been like following this for a while. Is there a specific point where we proved that our set of vectors spans P2?
Right. We did because we can write anything using these coefficients. You can write any polynomial as a linear combination of these x minus x1 squared, right?
Yeah. Do you get to call them vectors or polynomials, or either one works?
Either one works, I guess. Can we do a non-example, as in like something that is not a basis? Okay, let's see. Sure.
Should we do linear independence first and then do that?
Oh, yeah, sure. Okay. And then I will try to think of an example while we're doing that. Okay. So we have, this was just the particular example of a particular polynomial, but we can conclude that this basis spans P2. Okay, so we got that part. And then we want to know, is it linearly independent? And that is asking whether we can, C1 times 1 plus C2 times x minus 1 plus C3 times x minus 1 squared equals 0 implies, so given this, we want to know, do we have to have C naught equals C1 equals, oh, I switched the memory. Let's stick with the same notation. So C naught, C1, C2, all 0. If we do, then we have linear independence. If we don't, then we do not have linear independence. Okay, so we have already essentially done the work of multiplying this out. So I'm just going to use the work that we already did, right? So we did this multiplication of this same expression, but it was set equal to an arbitrary polynomial instead of just 0, right? So I'm just going to copy this and move it down here. Okay, so what I'm saying is that if you take C naught times 1 plus, okay, move it over a little bit, as C1 times x minus 1 plus C2 times x minus 1 squared, and you multiply it out and group the terms, this is what you get, right? This is just what we did to get this expression. And then what we get then, if this is equal to 0, then each of these C1 minus C naught minus C1 plus C2 has to be equal to 0. C1 minus 2C2 has to be equal to 0. And C2 itself has to be equal to 0. And then you can plug in. So knowing that C2 equals 0 implies that C1 equals 0. And knowing that both C1 and C2 equals 0 implies that C naught equals 0. So they're all equal to 0, right? Okay, so these are linearly independent. Okay, for a non-example, let's see.
Pardon me.
Yeah, go ahead.
Just real quick. They don't have to be. Oh, never mind. I thought before we were just like checking to make sure that there was only a unique solution.
Yeah.
But do the coefficients have to be 0? Like, does that have to be the unique solution?
Yeah, so when you're solving a homogeneous.
Oh, duh, I forgot how basic linear algebra works. Sorry, brain
Yeah,
broke.
that is, yeah, it is the case. But if you just know that it's a unique solution, since it's a homogeneous equation, it does have to be all zeros. Yeah. Okay, so yeah, we do have a quiz, so we should start that soon. I just wanted to say one thing relating to, sorry, it's slowly rotating. Okay, can you go back? Okay, relating to basis and span, just in general, and then I'll come up with a non-example that we can do next time as well. Let me write that down so we don't forget. So we'll continue on with this next week. But so when we're talking about a basis, right, that's a collection of vectors. So V1, p2, we'll just, let's just make it 3 vectors. Okay, so it has a certain number of vectors in it, and that's it. When we're talking about, and so the properties that it has are that it's linearly independent and it spans the space. And so when we write this, this only has 3 vectors in it. So if we were to consider, say, like the standard basis for R3, that's 1, 0, 0, 0, 1, 0, and 0, 0, 1. This is not equal to R3 itself, right? It's only 3 vectors in it, and R3 has infinitely many vectors. So when we look at it, it's just literally these 3 vectors in R3, the ones of length 1, right? And nothing else. But if we were to write the span of this, right, that is equal to R3 because the span includes not just those vectors, but all linear combinations of them, right? So the basis is not equal to the space. The basis is just some subset of vectors. And, you know, in this case, it's finite. So it couldn't possibly be equal to the whole space, but the span is equal to the whole space, right? So there's a little distinction that's good to know.
The basis is just a set of vectors. It's
Yeah, and some, like in this case, a finite set of vectors, yeah. Okay, so yeah, this is something to be careful about. Okay, yeah, so hopefully this is not too bad. I don't know if it's, would it be helpful to do some examples of like more examples, because we did do examples of like basis in Rn, but would it be helpful to do more examples of that along with like this abstract examples?
yeah.
Okay, yeah. Okay, I'll make sure to do that next time. Okay, so we do have to start the quiz. It should be it should become available at 1:30, so it's almost there. But I think I put it under, yeah. Oh wait, don't.
Yeah, it'll be unlocked at 1:30.
Yeah, I'm gonna try and change it really fast before you start it. Okay. There we go. Cool.